Let's talk about the rate law. Chapter 13, Section 3, the rate law of a chemical reaction. This section is entirely about the rate law. So the rate law can be defined as this. This is an example of a rate law. All right. Now the rate we did in a previous section. The rate is equal to the change in some concentration, let's say of A, over the change in time, and if it was disappearing, then we would say negative, right? Remember that? This is for a reactant. For a product, that's something that was appearing, we might have said the rate was equal to the change in the concentration of something that's showing up, right? Let's say X, we oftentimes use C or D, over T, right? That was the rate of a reaction. This was for a reactant because it was negative, right? And this is for a product because that's an arrow. It's supposed to be an arrow because it's negative, and this was positive because it was something that was showing up, right? So remember that, all right? That's the rate. That's the rate of a reaction, which we did in section 2. Now in section 3, we're going to talk about the rate law, okay? And then we're going to derive lots of interesting information from the rate law. So it's important. All chemists care about this. So an example of a rate law, if you have a rate which is dependent only on one reactant, then your rate law might be this, okay, where K is a constant. It's called the rate constant, all right, it's called the rate constant, and we just have to look that up, or we have to figure that out through some reactions or whatever, but for now, it's just a constant. This is some reactant. And this is a coefficient, which means that it's the order of the reaction. I said coefficient, I mean a superscript, right? It's an exponent, actually. So it tells us the order of the reaction. Now, another example of a rate law, if you have two reactants, might be this, where you have the concentration is raised to the M of A, and the concentration of B is raised to the N. Right? Here's another example of a rate law where we simply use different variables, okay? I would like you to sort of consider that these variables they're just placeholders, they're just variables. And so when I first wrote this one out a minute ago, when I was making the slide, I wrote rate is equal to K, A, B, and I wrote N and M, right? Because it doesn't matter, right? This is just the order with respect to A, which we'll explain more as this video unfolds. But then I realized that TRO uses M and N, and it doesn't matter, right? When I'm talking about this in class, I'm oftentimes going to use X and Y, and I might accidentally do it here when I'm doing this video because X and Y is what a lot of textbooks use. So these are 3 examples of a rate law, and I want to emphasize that if we're going to use the term rate law, what we mean is this: rate is equal to some constant times one of the reactants, right? And then the order with respect to that reactant, and then another reactant, M, and I just did it on accident. Look at that. I just did this N and M. So, all right? All right, so it's when you see the term rate law, please think about this form. Some picture that looks like this ought to come up in your mind when you hear the term rate law, okay? So, if the rate law can be described as K, right? If the rate law means rate is equal to K, A to the N, or if there's 2 reactants, it might be A and B, right? The rate constant, that term right there, is the K. A is the concentration of reactant A, okay? And N, here it is now, it is the order with respect to, in this case, if it were like that, it would be order with respect to A, okay? What do we mean by order? All right, reaction order. Okay, what we mean by that is that when we're calculating the rate law, or when we're calculating the rate, we use the rate law that's been determined experimentally or given to you, and then we use the K, which has been given to you, and we say if N is 1, or M in this case is 1, we would say that the rate law, so let me use an example here. If it's 1, we would say then the rate law, you can see this, right? It's just math. You would say then, all right, well, the rate is equal to K times the concentration of A. All right? If the order was 2, I'm going to use a different one, okay? Then we would say the rate was equal to K times B squared, right? Here we would say, now, this reaction is first order. Okay, and we're going to be doing this we're going to be using this language here for the next couple sections. First order. This, can you guess what this would be? If this is first order, can you guess what this would be? It's second order, right? Okay. Now let me say one last thing about reaction order, and then we're going to move on. The last thing I'm going to say is that if the rate law has 2 reactants in it, let's say A and B, then we would say this reaction, let's say N is equal to 1 and M is equal to 2. We're supposing this, okay? I'm making this up as I go, right? Giving an example. Suppose that N is equal to 1 and M is equal to 2. If that's true, then this reaction, here's what we would say. This reaction, can you read my writing? Is blank order. I don't have enough room here. With respect to, let's say A. This reaction is blank order with respect to A. You fill in the question. You fill in the blank, okay? First of all, say A. If I said A, this reaction is blank order with respect to A. What's the word that would go here? It's first, right? Can you see that? If N is 1, we would say it's first order with respect to A. What about B? This reaction, if I said instead B, I would say this reaction is blank order with respect to B. What would you say? It's second order with respect to B. Can you see that? Because if M is 2, 2 goes here, we would say it's second order with respect to B. Now what we would say if I said, not with respect to anything, but if I said this reaction is blank order, watch this now, overall. Overall, what can I mean by that? What order is it what order is it overall? Please pause the video and think about that and guess. This reaction is blank order overall. And if you said third, you win. Right? Can you see that? So the order of the reaction is essentially the sum of all the superscripts or the exponents of these reactants. Okay? So we'll be doing this more. You can pause this video or rewind it and listen to that part again, but don't memorize this part. Let's look at some examples first, and then you can decide if you want to look at that again. Of course, Tro has got all this information on page 525. Tro, it might help too, because he's obviously going to be more precise than I am, right? I'm talking sort of intuitively and feeling my way through it. Tro shows us on page 524 and 525. Okay, so let's look, I think, here now at what this might mean. The reactant concentration versus time. This is a figure that's on page 524. This is in Tro page, how do you spell page? Page 524, okay? Just want to walk you through it. It's not a real big deal. If we're talking about some reaction where the rate law is rate is equal to Ka 0, let's say that, okay? If that's true, you can see you know what this goes to? If you raise something to the 0th power times 1, right? Anything to the 0th power is 1. And so rate is essentially going to be K, right? And you know what rate means? Remember that? It's the change in the concentration. I'm going to use A because A is here. The change in concentration over time, right? and it's going to be negative because we're losing it, okay, is equal to K. Now watch this. I'm going to take my, if this is my y-axis, let's think about this like in terms of, let's say, y is equal to mx plus b, right? Let's think about it like that. And this is my x-axis. I'm going to want t to be over here by itself. Kt, right? Oh, that was over dt, right? Change in time, okay? Can you see this is essentially going to be, that's a minus. Minus a is equal to kt, or a is equal to minus kt. That's if this was 0th order, right? If this is 0th order, then we're going to have a is equal to negative kt. And that's exactly what we have here. We have a linear relationship between a and time, right? Can you see that? And what's the slope in this line here? What's the slope? Actually, I should put plus 1 here, right? Because that's the y-intercept. You see that? Okay. So anyway, this is the figure which is on page 524. It's decent to look at. It's not super important. Those of you who are looking for the bare minima, you can skip it. You can skip the next one too. I'm going to look at it, but you don't have to give much attention to it. This is also on page 524. This is the rate versus reactant concentration. So if we have a 0th order reaction, the rate doesn't change, right? Can you see that? The rate does not change. If we take the reactant concentration and take the rate, it doesn't matter what the reactant concentration is, right? Because for a 0th order, this just goes to 1, right? So this is essentially means rate is equal to K. It's not related to the concentration at all. If it's 1st order, we can see this kind of looks like y is equal to mx, right? Can you see that? Plus 0. So that's going to be linear. And if it's 2nd order, it's going to be quadratic. Okay? Now let's look, give an example. This is another figure that's in your book. This is an example, a really cool example of sublimation. But here's a 0th order process. It turns out, I'm just going to read this text to you here. A 0th order process. The figure legend here, figure 13.4, says when a layer of particles sublimes, and you remember what subliming is? Subliming is when something goes from a solid to a gas, okay? So when a layer of particles sublimes, another identical layer is just below it. Consequently, the number of particles available to sublime at any one time does not change with the total number of particles in the sample. And the process then is going to be 0th order. Okay, so if this is 0th order, then we would say that the rate of this reaction that we've got going on here is equal to K. Right? Well, let me just we had this in a previous slide, but which is equal to K times 1. Which is simply equal to K, right? So it does not depend on the concentration of the reactant for a 0th order process. Kind of a cool picture, I think. Okay, now let's talk about how we're going to take experimental data and figure this stuff out. So recall that we're talking about in this particular example, we're talking about a 1st order reaction, right? So look at this, the 1st order rate. The reason I know it's 1st order is because I'm about to figure it out, actually, okay? So let's say rate is equal to K. I'm going to say to the x. We're going to eventually find, by the way, x is equal to 1. Don't tell anybody I told you at the beginning, okay? This is 1st order. But here's how we figure it out. We say, all right, well, here's the initial rate. We know that rate, in this case, is equal to, right, that's the rate. I know it because it says it here, right? That's the rate. And here's another rate. Agreed? And here's a concentration of A, which I'm going to put in brackets here, okay? So it looks kind of informed like this up here, okay? The rate is equal to, watch this, K, and this is a constant, so it doesn't change. Now these are both true. The concentration is 0.1 in this first case times K, and its rate then is going to be 0.015. How do we know? Because we found this from experiment. These data are given to us as, can you read my writing? The question, here's the point now, to figure out reaction order, right? So these data are given to us to figure out the reaction order. Now I've already told you the order is 1. You're not supposed to tell anybody, right? Being a little bit silly there. Okay, so did you know that you can take two equations? If this is true, then the ratio of these is going to equal the ratio of those. Okay, I'm going to do this over and over again. So for now, just look at it. That means that 0.1 over 0.2 times K is equal to 0.015 over 0.030. All right, so we're taking a ratio. By the way, Tro goes through this entire process with you, okay? He goes through it on page 527. Actually, he goes through it before that. He goes through it on page 526. So I'm saying if this is true, I can take my K and just get rid of it. You see K is there and there? All right. Oh, I forgot to put X. Here's my X, and here's my X. Agreed? Okay. Now what I'm going to do is I'm going to take this equation and get rid of my X's here and put it out here. All right. And can you see that this reduces to 1/2? And this reduces to 1/2, right? So the question is, 1/2 raised to the X gives you 1/2. What is X? Can you see that X must be 1? Okay. If you can, you're done. Now the way that Tro solves it is he takes the logarithm of that. Okay, I'm not going to do the logarithm of this. It's math that you've done in order to get into this class. You demonstrated that you could do logarithms. That was part of your prerequisite. But I'm not going to do that for now. I'm simply going to feel my way through this. 1/2 raised to the X gives me 1/2. What is X? X must be 1. Can you see that by inspection? Okay, so let's do the same thing here. I'm going to go here. Let's do the same thing. This is the same problem, but we can do it for any ratio we want. Watch this now. Let's take this one now. Okay, this has a K in it. I did my rate law. Rate is equal to A to the X. Oh, sorry, K, rate A to the X. But when I do this, I can go ahead and cross off the X's for reasons which I showed you just a moment ago. All right, now if this is true, watch this now. This is raised to the X because this is my concentration, right? Is equal to rate. There's my rate law. It's just backwards, right? My rate is here. Okay, that term is there. So this is what it comes down to. Can you see this is 1/2? And this is 1/2. Can you see by inspection that X must be 1? Therefore, reaction is first order. Okay? All right, now let's consider higher order reactions, or lower order reactions, I guess. Okay, watch this. Let's do the same thing here. I'm going to take this one. I'm not going to. Well, yeah, I will explain it. I'm over explaining this. I know. Rate is equal to K. Right. So here's my rate. There's that term. So watch this. I'm going to take this and this, and I'm going to say, all right. Now it looks like this goes to be 1 over here. Can you see that? 0.015 over 0.015 is 1. So 1/2, this goes to 1/2, right? Can I just put that 1 and that 2? All right. 1/2 raised to the X gives 1. what is x? Can you see it has to be 0? X equals 0. Can you see that? Because that's the only x I can put in here to make this a true statement. Okay? So let's do you know what? Let's do this again here. Still 0th order. All right? Still 0th order. Do you see that? This is 1, because those two are the same. Okay? And this is going to have to be 1 also because it's equals, right? So it looks like it's 1/2. 1/2 raised to the x is equal to 1. X is equal to 1. You see it? Okay. I said I wasn't going to show you how Tro does it, but he's got it on page 526. Those of you who are feeling a little weak in spirit, you can ignore this, turn your ears off for just a second. I'll be fast. Here's how Tro does it. And it's clever. 1, right? 1, 2, raised to the x, right? Because we're always going rate is equal to k to the x. It's an x. Okay? That true 1/2 x is equal to 1. He says, all right, let's take the logarithm of both sides. The log of 1/2 raised to the x is equal to the log of 1, which implies that x log of 1/2 is equal to, and the log of 1 is 0, right? And so x is equal to 0 divided by the log of 1/2, which of course is 0. That's what Tro does. Okay, so let's do a second order one, and I think that we'll be done with that. Okay, I'm still going to feel my way through this. So all we're doing is 0th order, 1st order, and 2nd order. I think we're never going to need to be able to do logarithms. I don't think. You have to decide that, I guess. Okay, so remember that rate is equal to k. This is the rate law, the general rate law for some x order reaction, and we're trying to figure out the order. Well, okay, so the order is given to us right here as 2. Oh, now this goes to, and that's x, right? So this goes to 1/2 raised to the x gives me 1/4. Can you see that? Can you see why I'm going to ask you to inspect that? Do that by inspection. Can you see that x is going to have to be 2? All right. So that's how we do order with respect to particular reactant. Okay. So I think it's time to do an example. So here's an example 13.2. This is on page 527. All right. I'm going to do the same thing here I did before. And I'm going to say, all right, so I know this, that I'm going to come up here. Oops, no. Okay. Rate, watch this. Rate is equal to K, AX, BY, right? Now, what I'm going to do, when I've got 2 reactants, I'm going to take one that I know is the same, right? So that one's not changing. Tro shows you exactly how to do this, okay, on page 527, I think. He shows you exactly how to do this. So I'm going to say, let's take one where these don't change. So I chose 2 where one doesn't change, but the other one does. Watch this now. This is going to be, I'm going to call this X and this Y. Okay? Can you see that? So that's X and this is Y. Can you see then this comes out down to be, for this particular scenario, let's go 1 here, 1 here. This comes out to be 1/2 raised to the X gives me 1 raised to the Y gives me, what is this? 1/4. Right? Can you see that? It's 1/4. Now, it doesn't matter what Y is because that's just 1. So I can say, aha, 1/2 raised to the x is equal to 1/4. X is equal to 2. Okay? Now let's do one where these don't change, okay? So now I'm going to say, all right, I'm going to go with a different color. I'm going to go with blue. Let's say, all right, let's choose one where these don't change. Right? That'll be x. And this will be y. Okay? So it looks like, let's say this is part 2 here, okay? So it looks like 1 raised to the x, which we know what x is, but it doesn't matter now, right? 1 squared is the same as 1, over, or rather times 1/2 raised to the y gives me, and what's 0.082 times over 0.08? 0.0082 times over 0.0083. It's going to be, it's 1. Can you see that? It's 1. Really close to 1. Okay, so that said, can you see what y must be? This goes to 1. What is y? It's 0. Okay? So determine the rate law for the reaction. So the rate law now, we're ready to say the rate law. Rate is equal to K times nitrogen dioxide squared, right, times carbon monoxide to the 0, right, which is really K squared. Agreed? So there's my first answer. Rate is equal to that. All right? Now my second answer is easier. Rate constant. Now I got to figure out what K is. And that's very easy because I can just take any of my examples up here. And so I'm going to take my, let's say the first one. I'm putting boxes around the answer, okay? So let's take it doesn't even matter which one we take, right? Let's take the first one and say that the rate, which is over here, is equal to, and I'm not going to put the units in for simplicity's sake. We will, we do need to put the units in when we're done, okay? For simplicity's sake, we're not going to right now. 0.0021 times K times the concentration here, right? 0.1 squared. Can you see that? Then K is going to be 0.0021. I'm going to put the units in now. Molars per second over, and this was molar squared, right? And it was 0.1, so it was 0.01. Okay, so it looks like my answer, K, is going to be 0.21, and it looks like it's going to be 1 over molars per second. All right, so there's my second answer, the second part of this question. Okay? All right, hope that's helpful. And that's all we're going to do for this section.